In this lesson, we're going to discuss what exactly is probability. And I'd like to start with a story. The ranger was sent out to scout an invading horde of monsters. There were three possibilities. The horde was either large, huge, or massive. Given that each of these possibilities were equally likely, what was the chance that the horde was massive? In logic, statements are either true or false, and there is no in between. To make things numerical, a true statement can be assigned a value of 1 and a false statement a value of 0. But in reality, things are not always so clear-cut. Instead, it is helpful to have numbers between 0 and 1 that represent the information that is available about the truth of the statement. So a probability that a statement is true could be 10% or 65% or 1 over e or any other number from 0 to 1. The statement itself is either true or false. What the probability represents is the information about the two possibilities. A function can be defined more formally, but it is helpful to think of it as an operation, kind of a machine, that transforms values into other values. One of the simplest functions is the indicator function. The indicator function transforms the value true into a 1 and the value false into a 0. A nice thing that will come in handy later is that if there are multiple logical statements involved, indicator functions can be used to count how many of the statements are true. For instance, the indicator that 3 is less than 5 plus the indicator that 3 is less than 1 plus the indicator that 7 is less than 2 will be 1 plus 0 plus 0, which is 1, and exactly one of the statements 3 less than 5, 3 less than 1, 7 less than 2 is true. In general, if you have a finite set of statements, then the sum of the indicators of those statements counts how many of the statements are true. Now, another nice thing about indicator functions is that they can be used to indicate when events are disjoint or mutually exclusive. We say that events are disjoint or mutually exclusive, meaning that at most one of the events can be true at any one time. So for instance, if I say it's going to rain today or it's not going to rain today, those are disjoint statements because they can't both be true. In the story of the ranger from the beginning, the size of the horde would be either large, huge, or massive. And those three statements, the size is large, the size is huge, the size is massive, are disjoint events. Using indicator functions, this idea can be clearly expressed. While indicator functions are great if the truth or falsehood of a statement is known precisely, there are many instances where it is not known precisely. For example, something might not have happened yet, like the next presidential election in the United States. Or the statement could be about a physical system where small changes in the initial values lead to big changes over time. Flipping coins and rolling dice fall into this category. Another possibility is that the information is too expensive to obtain exactly. For instance, determining the exact number of people living in a major city can be very difficult to obtain. A probability function assigns some logical statements a number from 0 up to 1 that indicates the knowledge about the truth of the statement. Usually a blackboard boldface P will be used to denote this function. And as with indicator functions, the probability of a true statement is the same as the indicator of a true statement is 1, and the probability of a false statement is the same as an indicator of a false statement is 0. But a probability function could also have the probability of event S1 equals 0.3, or the probability of S2 equals 5/17 for some logical statements S sub 1 and S sub 2. When it is possible to assign a probability to a logical statement, we call that statement an event. In the ranger story, each of the three possibilities of large, huge, and massive for the size of the horde were equally likely. If the total amount of truth available is 1, and there are three possibilities, then the simplest way to divide the probability of truth is evenly among the three. In other words, each of the three possibilities should be assigned a 1/3 probability. In general, this idea is known as the principle of indifference. The principle of indifference says that if exactly one of S sub 1 through S sub n must be true, and there is no reason to believe that any one event is more likely than another, then for each I, the probability of S sub I equals 1 over n. The events that are assigned probabilities often involve sets, which are collections of objects which are called elements. Now, if an object A is in the set S, then we write A is in S equals true and call A an element of S. Otherwise, A in S is false, which we also write as A not in S equals true. That is, A is not an element of S. Oftentimes, we say that A is in S, we can say that S contains the element A. It's also sometimes, instead of saying the word set, we say the word collection. In mathematics, those mean the same thing. Now, a shorter way to write sets is to use set notations, where the elements of the set are listed out and surrounded by curly braces. So a set that contains the element red and green, but nothing else, could be written as follows. An important special set is the set of positive integers. And this set is usually denoted by left curly brace, 1, 2, 3, comma, dot, 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 right curly brace. A simple probability experiment comes from flipping a fair coin. A coin typically has two sides, one labeled heads for convenience and the other side labeled tails. If the coin is fair, then the principle of indifference holds, and each side of the coin is equally likely to come up when flipped. Another simple probability experiment is to roll a fair die. Die is the singular form and dice is the plural. One common type of die has 6 sides, each of which is likely to show on top of the die when rolled. The notation little d followed by the number indicates the outcome of a roll of a fair die with that number of sides. So for instance, d6 indicates a roll of a die with sides labeled 1 through 6. So if x was the outcome of the roll, it is always true that x will be in the set 1, 2, 3, 4, 5, 6, which can be written in shorthand as x is an element of 1, 2, comma, dot, 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 up to 6. Since this is always true, and true statements have probability 1, the probability that x is in the set 1, 2, 3, 4, 5, 6 equals 1. Because the die is fair, the principle of indifference applies. And for instance, the probability that x equals 4 equals 1/6, because there are 6 sides on the die. So to summarize, probability is interested in logical statements, things that are either true or false. And what a probability function does is take as input a logical statement called an event and returns a number from 0 up to 1, indicating the information about the truth of that event. See you next time.